This is Timothy Wood with the Citadel Civil Engineering Program. This is CVIL202 Statics, and in this lecture we're going to continue our discussion of 2D rigid body equilibrium, focusing primarily on free body diagrams. Again, free body diagrams are something we're going to use throughout our career as engineers, and so like in dynamics, we're going to be drawing free body diagrams all the time. We are doing rigid body equilibrium now, and we're talking specifically about free body diagrams. So let's lay out our steps to our free body diagrams. If we recall free body diagrams, we follow the acronym BEARD, and we're going to continue to do so. So the B in BEARD stands for body. And remember, we're now modeling these not as mathematical particles, but as rigid bodies, meaning that we're going to track both the mass and length of our objects, of our things. So that's the first thing we need to draw. The second thing we're going to draw is our external loads. And this is more complicated than it was when we were doing 2D. When we thought about 2D, our external loads were simply the forces, the body forces or the applied forces, and then the reactions typically coming from cables or something like that was pulling in a known direction. In this case, we're still going to have those things. So we're going to have our body forces associated with the mass, which in this case is almost always weight in this class. My electrical engineers might have electromagnetic forces that would fall into this class. There might be some other things. And then our applied loads. But now we know that our applied loads can take several different forms. They can be applied forces. So push or pulls modeled as concentrated forces acting at a point. They can be applied moments, either two forces equal in magnitude, opposite in direction, separated by a perpendicular distance, so a force couple, or just the straight up twist that we could apply at a mathematical point, applied moments, or we can have our distributed forces, which is what we learned about last time, where we actually deal with the pressure modeled as a volume, or if we're doing 2D, we'll take that slice and we'll turn it into an area where distributed forces has units not of kilonewtons, that would be applied force, or kilonewton meters, that'd be applied moments, but kilonewton per meter, which would be our distributed forces, or in US customary, we'd have pounds, pound feet for our applied moments, and pound per foot for our distributed forces. Again, our units are going to really help us understand what we're looking at in each case. All right, BEARD, so that gives us our body, our external loads, and then we would have our axes. And in 2D, we'll continue to draw our axes as most often as X, Y, and Z coming out of the board, or rotation about the Z in the counterclockwise direction. So this is BEA. R is reactions. And this is where free body diagrams start to get more exciting for us in 2D, because we have something new now. So previously, we said reactions are the forces where supports resist motion. And when we were doing 2D, that meant a force that was resisting motion, some sort of translation. So if the question that we'll ask ourselves is that if we need a force in a particular direction to resist translation, or if we need a applied moment to resist rotation. And then from here, we'll note that these things maintain equilibrium. And in most statics problems, we're going to have our applied loads acting on our rigid body, and we're going to be trying to solve for what these reactions are. Now, just to finish out our beard, the last thing we need is a D, which is the dimensions and labels on the system, knowing that both angles and lengths are going to be very important when we're labeling our system, to know what our lengths are, as well as to have everything labeled in terms of our overall system. Okay, one of the things to say about our applied loads here is that sometimes we will simplify our applied loads down to an equivalent system, an externally equivalent system, which will make solving for our reactions easier. It's not a necessary step, but sometimes it's helpful in particular problems. So the new thing here is really about doing these reactions. And so let's look at reactions for a couple of different connection types. We're going to take a look back at our video, our presentation here. So this is a structural reaction here. Then when we look at this, so the first thing we've got is we've got to acknowledge that when we're looking at reactions, we're zooming in on the reaction, on the connection to where it touches the ground, and we're thinking about, well, how does that reaction act on the body? Now, our natural tendency to say is that clearly it's not moving, so it's going to resist all the forces and all the moments. But what we have to recognize is that that's for the overall system. When we look at a joint by itself or a connection by itself, we're asking the question, how does this connection contribute to generating a reaction? It doesn't have to do everything, because most of the time it touches, a beam will touch the ground in multiple places, and those two reactions together will make sure there's no translation and no rotation. But we'd want to ask the question, well, which is this particular joint doing? So on this leftmost picture, you'll see the beam acting across the top, and it's connected to the buttress by what's called a rocker. And so if we look at a rocker, we might draw it this way. Sometimes it's called a roller. And schematically, the way that we draw this roller is like this, where we have the idea of a board sitting on a soup can, right? So the idea with a roller, so let's think about what kind of motions we would see out of this rocker. We're going to ask ourselves the question, does it resist translation and does it resist rotation? So if we look at this rocker, and again, something else is holding the beam in place, but right now if we looked at this rocker and we applied a lateral load on it, we'd ask the question, does it resist translation side to side? And if we look at this, it will actually rock. So it'll move side to side. There won't be a reaction force there. So it does not resist translation. Just like if you put a board on a soup can, it would make a very terrible skateboard. You would slide forward until you fell off, right? So that would be a bit of a thing. So no resistance to translation, no force. Now, if we look at it vertically, if we try to move it down, we would see that it would resist translation downward, because the bridge abutment is going to push back up, and that back up push is our reaction. So it resists translation down, which means we need an upward force. So if I were drawing a free body diagram of this roller, I would note that I need an upward force like this. And the key here is that this force is always perpendicular to the supporting slope. So I'm going to get a reaction force upward, like so. Okay. Now, when we think about this mathematically, it actually could be downward, but that would just come back as a negative value. Okay. And then again, we've always got to go back connecting our engineering and math model that will tell us whether or not this reaction force is up or down, and make sure through our mental model that the connection itself will resist motion up and down. For example, in this case, I think if the bridge tried to move up, it would actually lift off this support. So that's going to be a thing we have to watch out for. All right, we've done the two translation terms. So translate left and right. Does the force resist translation, or does it resist translation left and right? No, no force. Does it resist translation up and down? Yes, we get a force. Does it resist rotation? Well, no, it'll rock or roll. It's a rocker roller. So there's no moment there, which means that this is it for a roller, and we would get exactly one unknown. The idea behind a roller would be that when we think about our potential models that we might build for this, with a roller, it's just the same as a contact surface. It's just sitting on the contact. So if I have some platform here and I've got a roller, this would be a similar sort of roller. If I try to translate left and right, it'll slide, so there's no resistance there. If I try to translate down, it resists that translation, so I need that upward force, which we're seeing there. And then if I try to rotate it, it rotates freely, so there's no moment reaction. Okay, so that's a rocker or a roller. Now, in the right picture, we have exactly the same scenario, except it's a concrete beam sitting on a keystone. Now, one of the things that one of you is going to notice is that if we tried to rock it to the left, that you would see that gap close and the two things would press together. Or if I started to translate sideways, they would close and I would get a different reaction. I'd start to get a horizontal reaction or some resistance to rotation if I closed up that gap on the left. I'm speaking specifically about this gap here. But here's the thing I want to ask you, okay? Let's think of real quick about a 3D joint that I think most of us are going to have, which is our shoulders, okay? So we think about our shoulder and we see that it allows for rotation and it doesn't really allow for translation unless I move my whole body, but like no translation, but it allows for rotation. So it's like a ball and socket. It's exactly what it is. And we would say that all's fine and good and dandy in this range. However, I can actually get it to resist rotation, right? So if I get on the wrong side of the law, they're going to restrain me by taking my arm and putting it behind my back. And now we're at the edge of my rotation, right? I am no longer in a happy place because I have my arm cranked behind my back, right? And so we could say, well, now it's a fixed joint. Yes, so it's going to resist translation and rotation. That's kind of cool. However, I am not happy about this. And so when we're doing our designs, we want to make sure that our structures are kind of happy about what's happening to them. So in this example, if that beam was to slide to the left or to try and rotate up, we're now working outside of what we want the beam to do. We want the beam to just sit there, and if it's just sitting there, there'll be no lateral translation resistance and no resistance to rotation. It'll only have resistance from that little key in the vertical direction. So that's an important thing to think about when we're trying to build these mental models, is that we want to look at the connections within their normal working range. All right, let's look at another common connection type. This is called, unsurprisingly, a pin connection. A pin connection. And if we wanted to draw this pin connection in a diagram, schematic form, we would draw a triangle with the pin kind of at the top there. And then these lines, just like here, that's actually showing an immovable surface of some sort. And so if we look at this on the left diagram, we have a beam. It's pinned in place on a fixed vertical column. And so we're going to ask those questions again. Can it translate? Can it rotate about particular axes? Same thing in the right picture. They've come down and it's pinned here, and we're kind of looking along this beam that's being resisted in this 2D view. So let's ask the question. If I look at this pin, does it resist translation left and right? If I tried to move that bridge on the left to the right, that pin is going to stop it, right? It's going to keep it from moving. It's going to resist translation, and therefore, I'm going to need a force in the horizontal direction. Something like that. Okay? Because it resists translation horizontally. Can ask the same question. If I try to lift up or push down, will it resist vertical translation? And the answer is yes. It does resist vertical translation. Therefore, I need a force that's going to resist that translation. Lastly, I'll ask the question, does it resist rotation? Will it pivot around that connection? And the answer is yes, it will pivot around the connection. It doesn't resist rotation. Because it doesn't resist rotation, there's no moment. So let's look at another little model we might think about here. Here's my pin connection, okay? So I've got it in a fixed block. So if my left hand here is the fixed block and here's the rod, I can ask the question, does it resist translation? Yes, it resists translation side to side. So I'm going to get a force there. Does it resist translation up and down? Yes, I'm going to get a force there. Does it resist rotation? No. So I don't have a moment. So in the case of a pin connection, I'm going to have two unknowns that I'm probably solving for using my equations of equilibrium. So with the roller, we have one unknown. We know its direction. It's perpendicular to the surface. With a pin connection, we have two unknowns, perpendicular forces, resisting full translation, but there's no resistance to rotation, so no moment connection. So this is a pin connection. Our last connection type, oh, this gets me so excited. I love culverts. It's the thing I'm most passionate about in a technical field. I'm actually most passionate about teaching, but this is the next closest thing. This is called a fully fixed connection. fully fixed connection. And schematically, what we do is we just have our member and we draw those three little lines to indicate that it's just locked into an immovable object of some sort. So if we look at where that concrete box culvert top slab tees into the wall, this we would model as a fixed connection. And so let's ask our questions again. Does it resist translation? Does it resist rotation? So the first question is, does it resist translation? Will it resist being moved left and right? And the answer is yes, it's locked in there. And so we're going to need a force reaction in that direction to resist the left and right translation. Again, when we solve for our equations of equilibrium, the number could be a negative value, in which case the arrow flips around. Does it resist translation up and down? If I try to lift that slab up and down, does that wall connection hold it in place? And the answer is yes, it resists translation up and down, which means I need a vertical force as well. So I'm going to have two forces. It's not going to translate at all. And then finally, does it resist rotation? So is it going to rotate? And the answer is no, it's locked in there, so it's not going to rotate, which means that we're going to have a third reaction, a moment reaction. And so when we think about what our physical model might look like, it's going to look something like this. So again, here's my fixed block. It resists translation, so I need a left-right force. It resists translation, so I need an up-down force. And it resists rotation because it's fully locked in there, so I'm going to need a applied moment reaction there to resist that rotation, which gives me three unknowns. By the way, if we have a fully fixed connection like this, we call this resistance here. This is a cantilever. So we have a fully fixed connection with three unknowns. We might apply some loads out here, and that gives us a full cantilevered connection, which is a common structural detail. So these are our dominant forms of connection types in 2D. We'll work a problem together where we use these things. We can also have a cable, which is a lot like a roller. It's pulling in the direction of the rope, just like we had in 2D particle equilibrium. And then your textbook has a whole table in chapter 5 that outlines all sorts of other different interesting connection types, most of which we don't use, at least in civil engineering. My mechanical engineers might have a reason to use one of these weirder connection types, but these are our dominant ones in civil engineering. I look forward to working a problem together with you in class, and I'll see you then.